We want to find the domain of the given vectored valued function, where the domain of a vectored valued function is the intersection of the domains of x of t, y of t, and z of t, where x of t, y of t, and z of t are the x, y, and z components of the vectored valued function. So going back to our example, notice how x of t is equal to t cubed, y of t is equal to the square root of the quantity t plus 4, and z of t is equal to the square root of the quantity 5 minus t. So now we'll find the domain of x of t, y of t, and z of t, and then we'll find the intersection of all three domains, which will give us the domain of the vectored valued function. To help us do this, we'll look at the graph of x of t, y of t, and z of t. So here's the graph of x of t equals t cubed, where the domain is a set of all possible values of t, and notice how t can be any real number, and therefore the domain of x of t would be all reals. If we wanted to use interval notation, we'd have the open interval from negative infinity to positive infinity. Looking at the graph of y of t, notice how the possible values of t would be all the values of t that are greater than or equal to negative 4. So the domain of y of t, again, is t greater than or equal to negative 4. If we wanted to solve this algebraically without a graph, we'd have to recognize that the quantity t plus 4 can't be negative, which means it'd have to be greater than or equal to 0. So if we solve this for t, notice how again we'd have t is greater than or equal to negative 4. Using interval notation, we'd have the interval from negative 4 to infinity, where the interval would be closed on negative 4 and open on infinity. And then finally for z of t, again analyzing the graph, notice how the possible values of t would have to be less than or equal to positive 5. So the domain of z of t, again, would be t less than or equal to positive 5. Algebraically, we'd have to recognize that the quantity 5 minus t must be greater than or equal to 0. So if we add t to both sides, notice how we'd have 5 is greater than or equal to t, which is equivalent to t is less than or equal to 5. And again, using interval notation, we'd have the interval from negative infinity to positive 5, where the interval is closed on positive 5. Now let's go ahead and graph all three intervals on the same number line and determine the intersection of these three intervals, which will give us the domain of the vectored valued function. So let's let 5 be here and negative 4 be here. Well, first, the domain of x of t was all real numbers, or all reals, which should be the entire number line. The domain of y of t, t is greater than or equal to negative 4, so we'd have a closed point on negative 4, arrow to the right. The domain of z of t is less than or equal to positive 5, so we'd have a closed point on positive 5 and an arrow to the left. And again, we're looking for the intersection of these three intervals, where the values are in all three intervals. Notice how this would be the closed interval from negative 4 to positive 5. All of these values are in all three domains, and therefore this interval is the domain of the vectored valued function. So using step builder notation, the domain would be t such that t is greater than or equal to negative 4 and less than or equal to positive 5. If we wanted to use interval notation, we'd have the closed interval from negative 4 to positive 5. Because the interval is closed, we use square brackets. Before we go, let's take a look at the graph of r of t. The given vectored valued function would trace out this space curve. I hope you found this helpful.